or at least with me, and see what it is I'm trying. Okay, I will assume that that's not the case, and I'll continue. So what I will actually describe first is, this is something that I've looked at for quite a period of time. But actually it came out of another thing that I was involved in, and which is sometimes, because let me convince you of the following. So if I now blow up this thing here, then I have sort of the ball of radius 2, and I have the ball of radius 1, right? And I have this coefficient A inside, and I have my cloak here. What does it mean that U is equal to U tilde up here when I solve the Laplacian? Okay, what does that mean? Well, let's see what it means. So here I have my omega. And I now go out and solve with U is equal to phi. I go out and solve the Laplacian of U is equal to 0. I can do it. Now let's imagine that I have this thing here with a cloak and an A in here. So actually I look at this solution and I look at it now in B2 minus omega. So I have U is out here. Right? Let's now say I wanted instead to solve this equation. So I want to find U tilde. Well, let's say, and I want to have that U is equal to U tilde here. So I already know that I want U tilde, the U to be the U tilde here. How am I going to be able to do that? Well, so U tilde is going to be given here. So then I know that in here I have A. So I have to solve the equation in here, where I solve this equation here. So I solve divergence A grad U tilde is equal to 0 in B2. Right? And I solve it with a boundary condition given by U here. So I say I can do that. So now I have the U here as it should be. I've solved this equation inside here. Does that then mean that I have a solution with U tilde? Does that mean that I've now gotten a solution to all of this? Well, I certainly have a solution out here because A is equal to 1 out there, and I'm solving the Laplacian, so there's no question that I solve the equation with A out here. I also made sure that I solved the equation with A inside here, and I used the data from U as the data for solving this problem, and so I said U tilde is equal to U on the boundary of B2. So I took this data, so it's continuous across. But what is it that is required in order to have a solution of this in the large? What does it mean to solve this equation, not just in here and out here, but solve the equation across the surface? What does it mean to solve the second order equation across the surface? Well, you do it in a weak sense. It means that the field has to be continuous. So that's what I made sure, because I said U tilde is equal to U. But then I also have to have, when you look at the divergence form, you integrate by parts. You use Green's formula, it says that the normal component of the flux coming from the inside has to be equal to the normal component coming from the outside. So I actually have here, I have to have that if I take from the inside A, which is, the flux would be A grad U tilde dot N, that's when this would have to be equal to the field from the outside, which is grad U, A is equal to 1 dot N. So this is du dn. So if, when I solve this equation here, with U tilde is equal to U on the boundary, I get that the normal derivative is equal to the normal derivative for U. Then I have a solution everywhere. And that solution would be equal to U up here. So really what I have argued is that in order to make only changes locally in here, I need to have that the Dirichlet to Neumann data map, because this is Dirichlet data for you, tilde, this is Neumann data, and this is Dirichlet data for you, this is Neumann data for you. I need to have that the Dirichlet to Neumann data map for you and u tilde should be the same. So I need that, and I'll call it lambda A should be equal to lambda 1. And these are the Dirichlet to Neumann data operators. This is the one that maps Dirichlet data on the boundary of P2 to Neumann data on the boundary of P2. I mean, what I have done in a very difficult way is to tell you that the way this object here talks to the outside is just in terms of this boundary map, this non-local operator that's called the Dirichlet to Neumann data map on the boundary here. And if I take another object that has the same, it's the same black box, but it has the same Dirichlet to Neumann data map, then I can take this out and replace it by the other component, and the solution has not changed out here. Because I just solve it by solving it locally here, locally inside, and the fact that the Dirichlet to Neumann data maps, these non-local operators are the same, makes sure that the equation is satisfied across the boundary once I have imposed that they have the same Dirichlet. So that's really what is sort of, well, that's one of the elements of it, is that I can now go down and I can look at the ball of radius 2, and I could say what I really want to construct. So that's where I now want to take it. So any questions? So I will now take the following problem. I have reduced myself to wanting to solve in the steady state case the following problem. And I promise I will use slides at a certain point, but I do find that when going slow, it's typically a good way to do it because you slow yourself down and you don't flip slides quite as fast. So really what I want to do is I have this object here, which is a ball of radius 2. And I'm going to construct something in here, and I haven't told you how I'm going to do that, but I'm going to construct a flow in here. And then I have the A here. And then I have the other object over here, which is just 1 everywhere. And so over here, I'm solving Laplace u is equal to 0, u is equal to phi, this is in omega, this is in P2, and this is on the boundary of P2. And over here, I'm solving divergence A grad u tilde is equal to 0, u tilde is equal to phi, this is in P2, and this is on the boundary of P2. And then over here, I have lambda A of phi is simply equal to A grad u tilde dot n. That's the Neumann data. And over here, I have lambda 1 of phi. This is equal to du dn. That's the Dirichlet to Neumann data map that takes the Dirichlet data and maps it to the Neumann data. This is the map that takes the Dirichlet data and maps it to the Neumann data. Neumann data, by that I mean the cone 1 over derivative. And I want to construct it in such a way, I want to construct what I call the cloak. That's this part here. Such that lambda A is equal to lambda 1 for all A. So I want to give you one construction of this, so that independently of what you put inside, the Dirichlet to Neumann data map, when you look at it out here, give it any Dirichlet data, the Neumann data response is the same as you would have seen over here with just 1 in there. Because then I can replace, I can take down the space with 1 everywhere. I can take out the ball of radius 2 and I can replace this box by this box. And when I solve the corresponding elliptic problem, it hasn't changed outside. Because it's being solved in a weak sense by just making sure that I use the right Dirichlet data, because then the conormal derivative is equal to the conormal derivative here. And it's the only way to do it, to make it go all the way up for all data. So this is what I want to do. Okay. Now this is where it becomes interesting. I mean, so far we've just sort of introduced the problem. Now it's where it becomes interesting because this is actually a problem saying there is a converse to this thing, which is the whole problem in itself, which is actually many times referred to as a Calderon problem. And the Calderon problem, or Calderon's conjecture, this was a conjecture many years ago. Actually, this was the conjecture of Calderon's from, I believe it's from around 82, early 80s, at least that's when I saw the paper. So basically, there is a thing called the Calderon. I don't know, I don't like to call it the conjecture because it may not be true in all generality, and he certainly didn't say it that way, so I don't want anyone to come out and say it was proven this Calderon conjecture. But I'll call it the Calderon problem. And the Calderon problem is the following. So you can say, it says, is the following true? Is it true that, and now I'll use the notation I have here, so it's clear for everyone what lambda A is. Lambda A is the Dirichlet-Neumann data map for a particular coefficient A. And lambda B is equal to the Dirichlet-Neumann data map for a coefficient B, positive, definite, L infinity, so that you have an elliptic operator. Is it true that this thing here is equal to that? Implies that A is equal to B. That's Calderon, that's sort of Calderon's problem. And I mean, I'm being very vague, and I'm going to now want to quantify it a lot more and make sure that we get a precise thing. But see, this would sort of contradict cloaking, because cloaking would say that I could make lambda A is equal to lambda 1 for all A, in spite of the fact that, this A here is not 1. And here, I have this problem that sort of was posed by Calderon that said, is it really true that if I have two Dirichlet-Neumann data maps that are the same, then the coefficients are the same inside? And so, of course, if this is true, I can't cloak. And since I came here to give you a talk about cloaking, there must be something